Hi students, good morning. I hope you are all safe and healthy. I am Venkat, AS Physics course instructor, and welcome to week 8. In week 8, we are going to discuss on matter and materials, particularly stress strain graphs and Young's modulus. So you can copy the learning objectives in your copybook. So you also have got homework. You can pause the video and copy the homework in your copybook. So let's start with the strain. It's a familiar term to you. That is, strain is defined as the fractional increase in the original length of the wire. That is given by strain is equal to extension over original length. For example, if you put a tensile stress to a material, it will extend. So when it extends, we can calculate what is extension, and this extension over the original length will give us strain quantity, and it is a ratio of same quantity. Therefore, it has no unit. And strain is equal to, we can represent the extension using the letter X. So X over capital L, where capital L is the original length of the material. And also note that both extension and original length must be in the same units. That's what I have also told you. That so strain is a ratio, so therefore it has no unit. Sometimes strain is given as a percentage. For example, a strain of 0.012, which is equivalent to 1.2%. So stress is defined as the force applied per unit cross-sectional area of the wire. That is, when you put a tensile force on a wire, it extends. So we can calculate what is the stress. The stress is nothing but force over cross-sectional area. And this may be written as stress is equal to F over area, where F is the force applied on a material, and the area is the cross-sectional area of the wire, where F is the units of stress are newtons per square meter, because you know that force is measured in terms of Newton, and the cross-sectional area measured in terms of meter square. So the unit of stress is Newton per meter square. So this is equal to what we use for Pascal. So we can represent the stress in terms of Pascal also. And you know that this 1 Pascal is equal to 1 Newton per meter square. And we have a Young modulus, and the ratio of stress to strain is called the Young modulus of the material, and it is given by stress over strain, and in equation form, that is sigma over epsilon naught, where E is the Young modulus of the material, and sigma, that is the stress, and epsilon is the strain. The unit of Young modulus is the same as that for strain, because you know that strain has no unit, but stress has a unit that is equal to Newton per meter square. So Young modulus takes the unit of stress, that is equal to Newton per meter square or Pascal. In practice, values may be quoted in megapascal or gigapascal, and you know that 1 megapascal is equal to 10 to the power of 6. It's not 106. This is 10 to the power of 6 Pascal, and 1 gigapascal is equal to 10 to the power of 9 Pascal. And we have a graph for stress strain, and you know that here you will be able to see from the figure that is stress is taken in the y-axis, and strain is taken in the x-axis. And the stress strain graph until this point, the material obeys Hooke's law, and you know that the gradient of the stress strain graph will give us the Young modulus of the material. So now we have the definition for elasticity. The elasticity of a solid material is its ability to regain its shape after it has been deformed or distorted, and the forces that deformed it have been released. Tensile and compressive stress. Deformation that stretches an object is tensile stress, whereas compresses an object is a compressive stress. Now we have we will interpret the stress versus strain graph, that is stress strain graph. And you'll be able to see from the graph beyond point P, the line curves and continues beyond elastic limit E to the yield point 1, Y1, which is represented as Y1, which is where the wire weakens temporarily. The elastic limit is the point beyond which the wire is permanently stretched, and you know that, and it suffers plastic deformation. Beyond point B here, beyond point B, a small increase in the stress causes a large increase in strain as the material of the wire undergoes plastic flow. Increase of stress occurs at this point due to reduced area of cross section because we have stretched much until the wire breaks at B. The stress at B is called the breaking stress, and you know that this is ultimate tensile stress. And this, if you increase the force beyond this point, the wire will break. So we have also got the load extension graph. You can see from the figure that is, this is a load extension graph for a metal wire. If the wire is stretched beyond the elastic limit, the unloading line is parallel to the loading line. When it is completely unloaded, the wire is slightly longer, so it has a permanent extension. That's a deformation takes place if you put more force beyond the elastic limit. If you unload from this point, then the graph will be, it will go in the same line. But as you put more load beyond its elastic limit, there has been a permanent deformation takes place in the wire. And you also note that in figure B, it's the load extension graph for a rubber band. The extension during unloading at any given tension is greater than during loading. And as you can see from for this load, it extended more. For this load, in case of loading, it is extended less. So the extension during unloading at any given tension is greater than during loading, and the rubber band returns to the same unstretched length, but the unloading curve is below the loading curve except at zero and a maximum extension. The rubber band remains elastic, but it has a low limit of proportionality. And you also see that in figure C, it's the load extension graph for a polythene strip. The polythene strip has a low limit of proportionality and suffers plastic deformation as it does not regain its initial length that you'll be able to see from the figure. It does not regain its initial length. The extension during unloading, is greater than loading. So these are the interpretation from the load extension graph for a different material, that is metal wire and rubber band and the polythene strip. Next, we have a very important point that is about a rubber band. And you know that the rubber band, the work done to stretch the rubber band is represented in this figure. And you know that the area under the loading curve, is representing the area under the loading curve. This is the loading curve representing the work done to stretch the wire. And this work done by the rubber band when it is unloaded is represented by the area under the unloading curve. So this is the work done to stretch the wire, and this is the work done by the rubber band when it is unloading. And this area under the unloading curve represents the work done by the rubber band. And this is what, and this graph that represents when we put load on the rubber band, the work done on the rubber band is represented by this part of the graph. And when it is unloading, the area between the loading curve and the unloading curve therefore represents the difference between the energy stored in the rubber band when it is stretched and useful energy recovered from it when it unstretches. The difference is because some of the energy stored in the rubber band becomes internal energy of the molecules when the rubber band unstretches. That is what you're able to see from the figure. And this, how the area between the loading and unloading curve can be used to determine the internal energy retained when the rubber band is stretched and then released. That is what you are able to see from this graph. So this part of the graph, the area between the loading curve and the unloading curve, that represents the internal energy that is retained in the rubber band. The internal energy retained in the rubber band is represented by this part of the graph, and this is the loading curve and this is the unloading curve. And as you can see from the figure, the difference between the loading curve and unloading curve, that tells us the internal energy that is retained when the rubber band is stretched and then released. So now we have elastic potential energy. So we say that energy stored in a metal wire. So we can calculate this. We are going to derive it in the next part. The work done to deform an object is the strain energy. It is given by half Fx, or the strain energy per unit volume is given as half Fx over Al, where A is the cross-sectional area and L is the length of the wire. Or we can simply put it in this form, that is half times stress times strain. That is also strain energy per unit volume. And we have elastic potential energy. You will be able to see from the graph, it is the force extension graph. In the force extension graph, the area under the force extension graph, that tells us the energy stored in the wire. When we put load, the wire extends. Wire or the spring extends. When they extend, the energy stored in the wire we can calculate using the area under the force extension graph. So we have an expression for, or the method for calculating the elastic potential energy, that is given by, we have used two methods here. We can think about the average force needed to produce an extension X. The average force is half the final force, that is final force is F added to the wire. So we can write the elastic potential energy that is equal to work done on the wire. So therefore the final force, which is the average final force over 2, which is the average force, times extension, we get elastic potential energy that is equal to half F times X. And also we can use another method, that is the area under the graph, area under the force extension graph. So the area under the force extension graph, you will be able to see from the figure, it is the right angle triangle, and the area of right angle triangle is half times base times height. So therefore this gives the elastic potential energy as half Fx. We can also use another expression for calculating the elastic potential energy if we know the spring constant, because the F is equal to Kx. We know that the load is directly proportional to extension. So therefore we get the equation for a Hooke's law, that is F is equal to K times X. So if you plug in the expression of K times X in this half Fx, we get the elastic potential energy as a half Kx square. So we can use two equations interchangeably to calculate the elastic potential energy, that is half Fx or half Kx square. So both equations we can use to find the elastic potential energy of the wire when it is extended or compressed. So we have a problem solving. It is from the past paper question. An extension force graph for a spring is shown in figure. What is the spring constant of the spring? So we can calculate the force using the graph. We can calculate the what is the spring constant of the spring. So how we are going to use the graph? We know that the gradient of the force extension graph, that will give us the spring constant. But over here, the extension is taken in the y-axis and the force is taken in the x-axis. So first we find the gradient of this graph, that is extension force graph. So we use the expression F is equal to Kx, but K is the spring constant, that is equal to F over X. F over X. Therefore, we calculate the spring constant as 6 divided by 15. That is force times force over extension. Force is given, the maximum force added to the wire, that is equal to the spring. The maximum force added to the spring is 6 Newton, and the extension is given as 15 centimeter. So 6 divided by 15, we get the spring constant K is equal to 0.4 Newton per centimeter. Converting in terms of Newton meter, because Newton per meter, because the answers are given Newton per meter. So we should also convert this Newton per centimeter into Newton per meter. So converting centimeter, 1 centimeter, that is equal to 10 to the power of -2 meter. So multiplying this with 100, we get 40 Newton per meter, which is the spring constant. So the right option will be D. So we have also got another question from the past paper. A wire is extended by a force. The graph shows how the extension of the wire varies with the force applied. And you will be able to see from the graph, it is again extension force graph. And initially, a force W gives an extension D. Initially, the force W, this force W gives an extension D. The force is then increased to 2W. So the force is then increased to 2W. This increases the extension to 2D. So when you add, when you double the force, the extension also increases. That is equal to 2 times D. Which area of the graph represents the work done by the force when the force from W to 2W, when the force increases from W to 2W. So here, normally we take the extension along the horizontal axis and the force along the vertical axis. But in this case, the extension is taken in the vertical axis and the force is taken in the horizontal axis. But we can calculate the work done. That is, which area of the graph represents the work done by the force when the force increases from W to 2W. And you can see from the options A, that is given as ORQ and OQRS and ORS and TMRS. Now this, which part of the, or which section of the graph will give us the work done by the force when the force increases from W to 2W. So we have to consider this part of the graph, that is when the force increases from W to W. This part of the graph will give us the work done by the force. But since force is taken in the horizontal axis and extension is taken in the vertical axis, so we have to just reverse this, and which part of the graph will give us the work done by the force when the force increases from W to W. So if you reverse this, and you will get this TMRS. So TMRS, so this part of the graph, or this area of the graph, will represent the work done by the force when the force increases from W to 2W. Since the graph is since the graph in the graph, the force is taken in the horizontal axis and extension is taken in the vertical axis, we have to reverse this. Otherwise, just we always know that if the force is taken in the vertical axis and the extension is taken in the horizontal axis, then this part of the graph will represent the work done by the force. Since it is opposite, we have to take this part of the graph, that is TMRS is the TMRS, that area of the graph will represent the work done by the force when the force increases from W to 2W. So we have got another question. A metal wire is stretched by a load. The force extension graph is shown in the figure. What is represented by the area under the whole graph? The area under the whole graph, it is actually, now you see, before what we see in the graph, the extension is taken in the vertical axis and the force is taken in the horizontal axis. Now it is very clear. Now the force is taken in the vertical axis and the extension is taken in the horizontal axis. Now the area under this graph, that is the area under force extension graph, will represent the energy, that is the work done in stretching the wire. And that you can see from the options, the change in gravitational potential energy of the wire. So we are not taking the wire to different heights. we are adding load to the wire, so therefore the wire extends. So there is no change in the gravitational potential energy of the wire. And the option B, the energy that would be released from the wire if the final load was removed. So this is also wrong. And the energy is transferred in heat into heat energy in the wire. So this is not the internal energy when we put load in load on the wire. But this part of the graph, or the area under the force extension graph, will represent the work done in stretching the wire. So this will be the right option. So we have got another question, that is the Young modulus of steel is twice that of copper wire. So which means the Young modulus of steel wire is 2 times of copper wire. And yeah, and we have a length of the copper wire which is given as 50 centimeter, and diameter is also given for the copper wire, that is 2 millimeter, is joined to a 50 centimeter length of steel wire of diameter 1 millimeter, making a combination wire of length 1 meter. And you will be able to see from the figure, you can see from the figure, that is the copper wire and this is the steel wire, and the diameter of the steel wire is given, that is equal to 1 millimeter, and the diameter of the copper wire is also given, that is equal to 2 millimeter. Now if you relate both of them, the diameter of copper wire is 2 times of the diameter of the steel wire, and they have equal length. The 50 centimeter length of copper wire and the steel wire also has got the same length, which is also equal to 50 centimeter. Now both of them are joined, and they are then they have added the load to the both the wire. Any information about the load? No. So there is no information about the load. But the question here, the combination wire is stretched by a weight added to its end. Both the copper and the steel wire obey Hooke's law, which means it is not beyond its elastic limit. What is the ratio of extension of steel wire over ratio between extension of steel wire to the extension of copper wire? So these are the things you have to consider before you answer this question. One is you have to take down the Young's modulus of the copper wire. So the Young modulus of the copper wire and Young modulus of the steel. So now comparing both of them, you can see at the beginning the Young modulus of steel is twice that of copper. So Young modulus of steel is twice that of copper, and then we have to look at what is the length of each wire. The length of each wire is also given, that is equal to 50 centimeter for the copper wire, and even for the steel wire it is also equal to 50 centimeter. Then we need to consider the cross-sectional area of both the wires. The cross-sectional area of the copper wire is given as A, and we can calculate if we know the diameter or the radius. Since diameter is given, we can relate with them. We can calculate the cross-sectional area using pi d square over 4 expression. Then we are also given with the diameter of the steel wire. Sorry, the diameter of the copper wire is 2 millimeter, and the diameter of the steel wire is 1 millimeter. So we are given with the values of diameter of copper wire as well as steel wire. Now we will be able to calculate the cross-sectional area using the expression pi d square over 4. And now, so these are the data from the question, that is length of the copper wire, length of the steel wire, and Young modulus of the steel wire, Young modulus of the copper wire, and we have also got diameter, the diameter of the copper wire and diameter of the steel wire. Now we have to find the extension of each wire. So extension is not given, because you see that when you put a load to the combination of these two wire, we have to find the extension of steel wire and we have to find the extension of copper wire, and then take the ratio to get your answer. Now I have solved this problem in the same method. I'll show my working. You can see here what I have taken first. The Young modulus of the steel wire is 2 times of copper wire, and I have note down the length of the copper wire that is equal to 50 centimeter, and the diameter of the copper wire is also given, that is equal to 2 millimeter, and again length of the steel wire that is equal to 50 centimeter, and then the diameter of the steel wire is also given, that is equal to 1 millimeter. And now find the equation further. Now find the cross-sectional area of the copper wire using the expression pi dc square, d square over 4. D sub c representing the diameter of the copper wire, d sub s representing the diameter of the steel wire. So using this expression, we will be able to calculate what is the cross-sectional area of copper wire and the cross-sectional area of the steel wire. And we have also got another information, that is the diameter of copper wire that is equal to 2 millimeter, and the diameter of the steel wire that is equal to 1 millimeter is already given here. And therefore we can relate the diameter of copper wire to the diameter of the steel wire, which is equal to half of the diameter of copper wire that is equal to diameter of the steel wire. And we know the expression for Young modulus, that is E is equal to FL over AX. FL over AX, where we use the expression for the Young modulus that is equal to stress by strain, where stress is equal to force per area and strain is the extension divided by its original length. So taking the multiplying with its reciprocal, we get x E is equal to FL over AX. Here x sub s representing the extension of the steel wire, and in this expression I have written E s is the Young modulus of the steel wire that is equal to FL over AX sub s. So this x sub s representing the extension of the steel wire. So rearranging the equation to get extension of the steel wire, that is equal to FL AS ES, where ES is the Young modulus of the steel wire. And then it is similar to this expression for the copper wire. So therefore I have written XC, which is the extension of the copper wire, that is equal to FL over again A times EC. This EC is the Young modulus of the steel wire, not the extension. It's a Young modulus of the copper wire. This is Young modulus of the steel wire, and this is the original length of the steel wire, and the load added to the both the combination of wires are the same. And then dividing this expression, that is XS, that is extension of steel wire over extension of copper wire, we get this expression that is equal to FS LS divided by AS ES times the reciprocal of this expression, that is AC EC divided by FC. This is all copper, so it is represented as FC LC. FC LC is the length of the copper wire. Now you know that the length of the copper wire and the steel wire are the same, so we can cancel this, and both the wires are added to the same load, so therefore we can also cancel this FS and FC. So what are the remaining, what are the variables that are not constant and that are not same? And you know that the diameter is not the same and the Young modulus is not the same. So only we have the diameter. In this expression we have diameter, that is a cross-sectional area. In this expression we have Young modulus of the copper wire, and the same for the same for the steel wire. So the steel wire, the area, cross-sectional area of the steel wire, and this is the cross-section Young modulus of the steel wire. Now we get this expression as XS over XC, where extension of the steel wire over extension of the copper wire, that is equal to AC EC divided by AS 2EC. Why I have substituted here 2EC? You know that from here this ES is the Young modulus of the steel wire, that is equal to 2 times of EC. So I have changed this value as 2 times of EC. So ES has now changed as 2 times of EC. Now we can cancel EC because the numerator we have EC and the numerator we have EC and the denominator we have EC, so we can cancel this. So what are the variables left now? Only we have the cross-sectional area of the copper wire, cross-sectional area of the steel wire, divided it times 1 over 2. And you know that the cross-sectional area of the copper wire is given as pi dc square over 4, and the cross-sectional area of the steel wire is given as pi ds square over 4. So this pi by 4 and pi by 4 are constant, so it will get cancel each other if you divide AC over AC over AC over AS. So I don't want to include this pi over 4 in this expression. So I have got DC square, since this AC is directly proportional to this DC square. So I have written AC as DC square over DS square times 1 over 2. And I have also converted this DS to DC over 4. Why? Because you know that the diameter of the copper wire that is equal to 2, I have written here, the diameter of the copper wire that is equal to 2 millimeter, and the diameter of the steel wire that is equal to 1 millimeter. Therefore, the diameter of the steel wire is nothing but DC over 2. That is half of the diameter of the diameter of the copper wire that is equal to diameter of the steel wire. So ds square here that is equal to dc over 2. So squaring it will get dc square over 4. Now we have got 4 in the numerator, and in denominator we have 2. So 4 over 2 that is equal to 2. That is the answer. And this is a very big working, but we can do this question in a shortcut using a shortcut method. The shortcut method is very simple now. So what is the shortcut for calculating the ratio of these two quantities? That is extension of the steel wire to the extension of the copper wire. Now you represent here the extension of the steel wire that is equal to 1 over ds square es. So why I have used 1 over ds square es? Because first we have to identify the question. The force for the two wires are the same. So anyhow, if you put it in the equation, it will get cancel each other. So we have to remove the force immediately. And one more factor for the both wires are the same, that is equal to its length. So I don't want to include the length in my equation. So I have written directly xs is equal to 1 over ds square times es, because the diameter of the steel wire is different from the diameter of the copper wire, and Young modulus of the steel wire is different from the Young modulus of the copper wire. So I have to include this in my equation, but I can remove the force and the length. And I have also got the expression for the copper wire, extension of the copper wire, that is equal to again 1 over dc square ac, because this extension and the diameter, they are inversely proportional. That is square of the inverse proportion. So therefore, since AC is equal to pi d square over 4, so we have an extension of the copper wire that is equal to 1 over dc square EC. Then multiplying with its reciprocal, we get xs over xc is equal to dc square EC divided by ds square ES. Now it's very simple, because dc square, you know that dc square is equal, dc is equal to 2 millimeter. Squaring it, it will become 4. And ds is also given, that is equal to 1 millimeter. So squaring it again, it is going to be 1. And the relationship between the Young modulus of the copper wire and the Young modulus of the steel wire, which is also at the beginning itself we have written, that is ES is equal to 2 times of EC. So substituting the ES is equal to 2 times of EC, we get EC will get cancelled. Therefore we have got 4 over 2, and xs by xc, this is extension of the steel wire to the extension of the copper wire, that is equal to 2. So this will be the right answer. We'll check in the question now. So 2 is the option B is the right answer. So this is how you have to solve problem. And before you answer question, just especially in the case of taking the ratio of the quantities, so which are the variables you can remove in your equation? So first identify those variables, then you write your equation, then it will become very easy for you to solve problems. That's all we have in this chapter. Thank you. Keep learning and keep doing good.